Hey there, chemists. How y'all doing today? Doing good on what feels like day 1000 of this quarantine, but still learning chemistry, still kicking butt with all our labs and all of the cool stuff we're doing at home that I'm sure you are. Today, the question is, what is your favorite scientist? Rather, who is your favorite scientist? Just because I'm so curious, kind of a mild question today. Let's see here. Let's make sure my mic is okay. So it sounds like people can hear. But once again, the question today is, who is your favorite scientist? Go ahead and write that in the chat box. For me, I'm also going to kind of go mild with this. Antoine Lavoisier. Lavoisier. He was a French nobleman. He's considered like the founder of chemistry, and there's a lot of really crazy stories about Antoine Lavoisier, but he was one of the French noblemen right at the rise of the French Revolution, and so we know what happened with those people. So if any of you have any favorite scientists out there, go ahead and put them in chat while we're waiting. Some other things that you may or may not know, down below, I have posted my slides. It's on the button that says slides right below my face. And if at any point today you want to ask a question, feel free to do so in either the comment section over on the right or in the ask a question section down below. What I like to try to do is kind of make my way through the lesson and then pause for a question. So if I don't get to your question immediately, don't worry. I promise I'll try to come back to the questions that I'm sure you may have. So today we are going to get started with Unit 4, Chemical Reactions. A fantastic unit in the world of chemistry. I really love this unit. It is a hefty unit, though. There is a lot of stuff that we're going to be talking about in today's lesson. So once again, if at any point you have any questions, feel free to write them down below or in the comment section over to the right, and I will do my best to answer them. And if you think about your favorite scientist, you can put it over to the right, too. Just a few announcements. First off, we have some more AP CRAM reviews. We're doing kinetics on the 28th and thermodynamics on the 30th. And May 5th, we're going to be doing our last lesson worth of material on equilibrium. And then we'll do some practice after that, along with a large Ask Me Anything AMA the day before the test. Don't forget, we also are doing the AP Olympics starting early May. You should have gotten emails. You can join to win some prizes and kind of do some cool review stuff along the way too. Any other information, as you guys know, all those social media website things right there. And today, this is what we're going to do. So first off, we're going to start with patterns of chemical reactions. Basically, what we're going to be looking at is like why certain chemical reactions happen the way they do. We're also going to be looking at the products of certain chemical reactions. We're going to move on to types of chemical reactions and also look at net ionic reactions, which I know some of you love so very much. We're going to end today's session with stoichiometry and titration. So today, at the end of the session especially, we're going to be looking at and using periodic tables a lot. So please pull that out if you don't already have it. Have a calculator ready, pen and paper. Always write down the information as much of it as you can. But once again, anything that you do miss, they're on the slides, which are listed down below. Let's go and get into it. So chemical reactions. As I'm sure a lot of you guys know, a chemical reaction is vaguely defined as when a chemical changes into a different substance. Now, we also have physical changes as well, and that's going to be when a substance changes state. But the big thing a chemical reaction needs is the change in identity of the substance. So if the name of the compound is different on the reactant and product side, then it's a chemical reaction. As far as chemical reactions go, bonds break in the reactants, the atoms tend to rearrange, and then bonds form to make the products. Now, there's a lot of different types of reactions. We can have individual atoms coming together to form products, or we can have decomposition reactions where the reactants will break apart and not form. But the general flow of a chemical reaction is atoms break apart, they rearrange, and then they reform to form those products. And of course, our classic chemistry cat down below. I feel like this wouldn't be a good chemistry stream, especially in terms of chemical reactions, if I didn't talk about balancing reactions. Luckily, I don't think there's going to be a direct balancing chemical reactions question. We balance reactions in order to satisfy the law of conservation of mass, which states that matter cannot be created or destroyed in any process. Matter in the universe must remain constant. And that's technically for normal chemical reactions. There are nuclear reactions or transmutations where the matter can change in terms of the nuclei of atoms, but luckily nuclear chemistry is not a part of the AP curriculum. And we know that a chemical reaction is balanced when the number and type of elements are equal on both sides of the reaction. I think that there are so many ways to have and to balance chemical reactions. There's a lot of tricks, but one of my favorite tricks is to balance the element that appears the most, just like literally written in the equation, the last. Balance the, little tongue-tied there. Balance the element that appears most last. And yeah, it definitely does balance and play into stoichiometry. You need to have a balanced chemical reaction in order to do stoichiometry. Luckily, they almost always give us a balanced chemical reaction. So here's an unbalanced chemical reaction. It's the combustion of methane, CH4. We have carbon appearing once on the left and once on the right. We have hydrogen appearing once on the left and once on the right. But we have oxygen appearing a total of 3 times. Once in the oxygen molecule, once in the water molecule, and once in the carbon dioxide. So because it appears the most, I'm going to balance it last. I start off by balancing the hydrogens, adding a 2 in front of the water molecule. This allows for me to have 4 hydrogens on the left and 4 hydrogens on the right. And then I finish off by balancing the oxygens. There was a total of 4 oxygens on the right-hand side of the molecule. I added a 2 in front of the oxygen gas in order to finish it off. One thing that I always do when I'm balancing chemical reactions is when I come to the end, I just double check that everything is balanced. 1 carbon, 1 carbon, 4 hydrogens, and 4 oxygens on both sides. It's a good practice just to kind of get to the end and be like, okay, that's balanced. One last trick for you AP Chem kids and possibly teachers if you're out there watching. I generally see like if there's a coefficient in the balanced chemical reaction, it's probably balanced. So where this starts to get a little bit more important and relevant to AP chemistry is actually predicting the products of chemical reactions. And for you guys out there, given the reactants of a chemical reaction, you should be fairly comfortable at predicting the products, meaning figuring out what should come out when you mix 2 things together. And notice that I said most inorganic reactions. Organic chemistry, you literally spend an entire year figuring out how to figure out the products for organic reactions. So generally speaking, when an inorganic reaction occurs, the cations will replace the cations and the anions replace the anions. A lot of your teachers probably went ahead and said metals replace metals, nonmetals replace nonmetals. That works well too. And essentially, what we need to consider is that all of our ionic formula writing rules apply to this section. Remember that we form ions based on the rules established earlier. The formula of an ionic compound represents the smallest whole number ratio of ions in the compound. So, for example, if I were to bring magnesium and chlorine together, you would get MgCl2. because you would have 1 magnesium with a 2+ charge for every 2 chlorines with a 1- charge. Generally speaking, knowing the names of formulas and ionic compounds is helpful and makes you move faster through the test, but it's not a requirement. It's one of those things that if you know and can see ionic and covalent compounds in terms of their names, you can answer questions more quickly. But one of my students in the past that basically like came out and said, hey, when we did nomenclature and like polyatomic ions and you making us memorize those, I felt like that was kind of unnecessary. And I was like, but knowing them made you move faster through the test. And he was like, yeah, that's actually true. Last but not least, you do want to know the diatomics. These are, whenever you're writing them by themselves in a chemical reaction, you always kind of slap a subscript 2. So oxygen never exists by itself. It's always O2. Hydrogen never exists by itself. It's always H2. Now, I shouldn't say never. There are situations where you can have atomic oxygen and atomic hydrogen, but the language of the test and the question will be very explicit, and you will know that you're dealing with a single oxygen atom or a single hydrogen atom. So generally speaking, if you see oxygen gas, you know you should put O2. So the first kind of reaction I wanted to look at here was, let's say we mix magnesium and oxygen together. We know that the only 2 things that a metal and a nonmetal can do is combine to form an ionic compound. Magnesium generally forms a 2+ charge, while oxygen normally forms a 2- charge. That means when they form the ionic compound, when magnesium and oxygen react with each other, you'll go ahead and get MgO. Notice that when I'm doing this, I never consider the amount of chemicals on the left and right-hand side. I am only considering the charge of elements and whether or not they are diatomic if they are by themselves. I only spend the time to balance the chemical reaction after I have predicted the product. And that should be a 2 in front of the MgO. That should have been a 2 in front of the MgO. Let's see how quickly I can change this here. Boom, 2. Let's continue to present this here. I feel like that was pretty quick. So, perfect. So once again, that I never consider or try to balance a reaction while I'm trying to predict the products of the chemical reaction. I always predict the product first, and then I balance at the end of the reaction. So I have 2 more examples here. The first one is silver nitrate reacting with sodium chloride. I know that silver and sodium, both being positively charged ions, are going to replace each other. And the nitrate and the chloride are going to replace each other because they are anions. The other way I like to look at it is this. If I were to separate the ions, I know that Ag is positively charged. And if this chemical reaction is going to occur, is it going to want to bond with the positively charged sodium or the negatively charged chlorine? Opposite charges attract, so it's going to want to form a bond with the chlorine. I go ahead and form AgCl. It's a 1-to-1 ratio. I go ahead and form NaNO3. It's a 1-to-1 ratio. And what's really nice about this particular chemical reaction is that after I do this, the replacements, the chemical reaction is already balanced. Now, I specifically chose this next reaction mostly because I wanted you guys to look for something important. First off, what's really fun is that alkali metals, when you place them into water, they explode, as I'm sure you all know. Gotta love explosions, right? I want you guys to always consider water as H+ and OH- in terms of chemical reactions. Now, water is 100% a covalent compound. It is not ionic. We do not have a hydrogen ion bonded to a hydroxide ion. But when dealing with certain types of chemical reactions, it is helpful for us to understand that the hydrogen can move away from the hydroxide in the water molecule as if it were ionic. What this kind of allows for us to see is that lithium, which is normally a positively charged ion, which will form, a positively charged ion, will want to form a bond with the hydroxide. Hydrogen is left by itself, and as we all know, when hydrogen, a diatomic, is left by itself, it gets written as H2. So the products for this chemical reaction end up being LiOH and H2. This is one of the more frustrating balancing reactions, and sometimes when I get into balancing, if I get too far ahead of myself, if I don't like take a step back and kind of go, okay, what do I need to do? I will literally just erase all coefficients and rewrite it. But the balanced chemical reaction has 2's in front of the first 3 compounds, and then the H2 is all by itself, okay? And this is where I'm going to kind of pause here and answer some questions. It will be kind of a quick moving session today, mostly because we have a lot to talk about. But Perla has asked a question in regards to, aren't they aqueous though? I thought that was because they were ions. And right now, all I'm doing is trying to establish some patterns in chemical reactivity, meaning that when an ionic reaction occurs, the ions will separate in water, sure. Water does not self-ionize very much, so water is not aqueous. Water is water. Water is liquid. Water is a covalent compound. So it doesn't exist as H plus and OH minus when dissolved in water because it is water. And the substance H plus. So first off, what I did is this reaction on the right-hand side is a redox reaction. It is an oxidation reduction reaction where electrons are transferred between the thing. But yeah, you can't leave H plus or just H by itself. It is one of the diatomics, so it has to be written as H2. Yeah, exactly. All right. Promise, once again, if any of these questions come up later, we'll go over them. But as we kind of work through some of these chemical reactions, I'll keep bringing up the patterns of reactivity that we've established at the beginning. So moving on, AP tests us fairly extensively on 3 types of inorganic reactions and 1 type of organic reaction. And you're probably going like, wait, there's an organic reaction we had to know? And guess what? Yeah, you did. It is the combustion reaction. We all know and love combustion, and I'm sure if I gave a combustion reaction to most of you, you'd be fairly comfortable identifying it and identifying the products of it. The 3 inorganic reactions that we will see are precipitation, acid-base reactions, and oxidation reduction reactions. The fun thing about combustion reactions is that they are also a special type of redox reaction, oxidation reduction reaction. So that's also where sometimes teachers will throw that discussion in, okay? But of course, this says here how chemical reactions occur. It's kind of hard to read. It says, we're moving a proton, that's the red one. We're moving an electron, that's the green one. And of course, the blue one says magic. Magic is just unexplained science, guys. Yes, you will absolutely have to identify when it is a precipitate versus when it's soluble, which we'll talk about when we get to precipitation reactions. So first one off is combustion reactions. A combustion reaction is going to be when a organic molecule, organic, remember, just means that it contains carbon, reacts with oxygen gas O2 to form water and carbon dioxide. And hopefully you are fairly comfortable with the fact that combustion reactions are very exothermic and they release a lot of heat and light. And probably one of my favorite combustion reactions ever, it is the combustion of propane. Gotta love my barbecue. Basically here you can see that the oxygen gas reacts with the carbon and hydrogen to produce a lot of CO2, H2O, and heat. And we use that heat to make our hamburgers. That's right. We have a lot of graphs today. Why do I love chem class? That's right, combustion reactions. Did any of you guys in your chem class see like methane bubbles or the oxidation of the gummy bear? I do that with my students. It's super fun. All right. Maybe I can find some videos of it and post it in our next upcoming sessions, Perla. All right, so the combustion I think is fairly straightforward. You do want to be comfortable with it. There is combustion analysis type problems, which I can kind of throw in one of our upcoming ones. But yeah, that's pretty much it. We know that a combustion reaction will produce CO2 and H2O. Precipitation reactions are next. And these are a lot more common for us to get a stoichiometry type question. So first off, the word precipitate means solid. And generally speaking, we're going to have a precipitation reaction when we mix two solutions together. Two solutions will mix together and out pops a solid. We talked about ability to dissolve last week. That's referring to solubility. And ionic compounds are mostly soluble in water, but there's a handful of insoluble salts that you should keep on the back of your mind. Obviously, in a precipitation reaction, the product that we make is insoluble in water. And you have to memorize these 4 salts because these 4, not salts, excuse me, ions, which will then make a salt, because these 4 sets of ions are always soluble in water. So if they are bonded or combined with something, then you know that that substance is going to be aqueous. You know that that substance is going to be aqueous. So let's go ahead and check this one out. We have lead nitrate. We know it's aqueous because it's bonded to nitrate. And potassium iodide, we know this is aqueous because it's got potassium in it, are reacting with each other. Our general rules and patterns of reactivity tell us that the cations will replace with the cations and the anions will replace with the anions. So we should end up with lead iodide and potassium nitrate. The lead bonded with the negatively charged iodide, the potassium bonded with the negatively charged nitrate. Now, based on these 2 products, only one of them is soluble in water. And if you notice, the KNO3 contains an alkali metal and nitrate, meaning that the product on the far right side will be soluble. If they identify the reaction as a precipitation reaction, then you know that the other product, PbI2 in this situation, is going to be the solid. It is insoluble in water. And that's when we go ahead and slap the S sign. S means solid, not soluble. That's a big mistake that a lot of students kind of make, and it's by accident. And then, of course, last but not least, we go ahead and balance the chemical reaction by putting a 2 in front of the Ki and a 2 in front of the KNO3. Now, a lot of you guys probably did these kinds of chemical reactions in class, and you collected the products via gravimetric analysis. So I just want to quickly show you what that looks like using my whiteboard. So I'm going to move over here. So basically, when we do this, generally speaking, you have some salt dissolved into a beaker or a flask. And in this situation, it would have been PbNO3. In another beaker or flask, we have the other salt. I know, my lovely drawings here. I should go professional, but I just love chemistry just so darn much. With the Ki, and I realize that it's not focused. I want to go ahead and make sure it's focused there. And essentially what we do is we mix these 2 solutions together. And when we do this, the salt that is insoluble precipitates out of solution. So we go ahead and get, once again, we still have a solution, but we get the insoluble salt solid on the bottom. And lead iodide is great because it's this beautiful yellow precipitate. So we're going to label it yellow, and it's solid. And then the KNO3 is just still dissolved into solution, KNO3. What we can then do is take this solution here and pour it into a funnel with a filter paper, and essentially, there we go, collect in the filter paper the lead iodide, There's that yellow lead iodide. And then in the bottom, we collect the solution of KNO3. So all that gets filtered out. And they always ask like lab questions about this, and probably the easiest answer is that the salt is still wet, and you need to make sure to completely dry it. So that's one of those ones that you should always keep on the back of your mind. Awesome. Yeah, and you probably did this first semester too. It looks like a lot of you guys remember it. And yeah, all right, moving on. So that's precipitation reactions. Let's go here. Up next is our favorite acid and base reactions. So now, while the section of acids and bases are not on the test in terms of Unit 8, Unit 4 does briefly talk about neutralization reactions and titrations, and we'll get to titrations at the very end. You also want to have a basic working definition of what acids and bases are too. Acids are going to be substances that donate protons. Remember, protons are just hydrogen ions. Oftentimes, chemicals that are acids have the H in front, so we can have like hydrochloric acid or acetic acid. Notice that even in acetic acid, the hydrogen that's written in front is the one that's acidic, and there's a couple of non-acidic hydrogens in the back. Bases are going to be substances that accept protons. Generally speaking, there are two main types of bases you want to look out for. The first and probably most common one are going to be metal hydroxides. Metal hydroxides are going to be like lithium hydroxide or calcium hydroxide, where you have an ionic bond between a metal and the hydroxide polyatomic ion, OH-. Now, in terms of an acid-base reaction with an acid and one of the metal hydroxides, the substance that accepts the proton is the hydroxide polyatomic ion. Now, the other lesser common type of base, but still probably relevant and important in your world, are going to be the molecules that contain nitrogen. Two examples of this would be ammonia. And remember, molecule refers to something that is covalent. So NH3, ammonia, is really good at accepting hydrogen ions. Or methylamine, and the nitrogen that is bonded to the carbon has a set of lone pairs, negatively charged electrons, that attracts hydrogen ions fairly well. So that methylamine can accept protons and does act as a weak base. Now, as far as the acid-base reactions go, there are a couple of things that you need to make sure you're comfortable with. And the first one is that when they ask you what an acid-base reaction is, all you have to say is that a proton was transferred from the acid to the base. The most common type of acid-base reaction that they ask about are going to be regular acids reacting with metal hydroxides. And these chemical reactions will always make salt, which is just a fancy word for ionic compound, and water. So let's go ahead and look at potassium hydroxide. When potassium hydroxide reacts with sulfuric acid, H2SO4, we know that, and let's kind of look at this two ways. This is a metal hydroxide is the KOH, and the acid is the H2SO4. So I already told you that the products are going to be salt and water. Okay, so H2O is going to be one of the products. But let's go back to our patterns of reactivity. We know that the positively charged ion will want to bond with the negatively charged ion and vice versa. So what we should end up seeing is that the potassium ion, the K+, will want to bond with the SO4 2- and form the ionic compound K2SO4. H+, which is a +1 charge, will want to bond with the OH-, which has a 1- charge, and form the water. So once again, everything that we spent the first 10 minutes of our session talking about in terms of flipping partners still applies here with acid-base reactions and even with the precipitation reactions before. Balancing this reaction, we need a 2 in front of the KOH and a 2 in front of the H2O. The last type of reaction is, I feel like, the one that has the most fear around it, and that's the redox reactions or the oxidation reduction reactions. I actually really like these. I don't think that they're too bad. As long as we have and cool, awesome favorites, awesome. Unless that's sarcasm. Uh, um, I don't think that they're too bad as long as we come kind of awesome. I love that. I love that it's your favorite. I don't think that they're too bad as long as we have a few rules down and establish a few patterns with these things. Okay, so an oxidation reaction is going to be in a reaction where electrons are moved. Once again, going back to acid-base was protons, so therefore redox reactions or oxidation reduction are going to be ones where electrons are moved. And hopefully you all have the mnemonic oil rig. Some teachers use Leo goes grr, Leo the lion goes grr. I just stick with oil rig though. So oil rig stands for oxidation is losing electrons, and rig stands for reduction is gaining electrons. And what I think is probably the more important part of this is the second half, which I've written on the right-hand side. When something loses electrons, the substance becomes more positive. When something gains electrons, the substance becomes more negative. Hence why we use the word reduce. Reduce is indicating that the charge or oxidation state of the substance is becoming less. It's reducing. And that's kind of where the language comes from. Oxidation is losing electrons, reduction is gaining electrons. Now, in order to balance a redox reaction, we do need to determine the oxidation numbers. And as far as this goes, really at the end of the day, you can determine that you have a redox reaction if the oxidation numbers of the reactants change when they go to the products. For acid-base reactions and precipitation reactions, the redox numbers oxidation numbers do not change. And therefore, if the literally, if the redox oxidation numbers change, you know it's a redox reaction. So I listed my favorite rules here. There's a couple of other like nitpicky rules, but if you have these 5 down, it will get you through like 98% of the oxidation type problems. In your textbooks and online, there's probably a lot longer lists. So if you have like all the time in the world to study for AP Chemistry, I'd go look at those. But once again, this will get you through 90% of the oxidation number assigning. Oxidation numbers for atoms and their elemental form is 0. Some examples include solid sodium, oxygen gas, or even elemental sulfur, which is S8. In each one of these situations, the oxidation state is 0. The charge of a monatomic ion is equal to the oxidation number. One thing that a lot of students misconstrue, or one thing that a lot of students, I think, trip up is that oxidation number is the same thing as charge. And that's not true. Remember, atoms and covalent compounds are not charged, but they can have oxidation numbers. It's just that in a lot of ionic compounds, the oxidation number is equal to the charge of the substance. So for example, in aluminum chloride, an ionic compound, Al has a charge of 3+, and that means the oxidation number is +3. In terms of chlorine, the chloride ion is 1-, and therefore its oxidation number is 1-. As far as our molecules or covalent compounds go, the oxidation states can be pretty much figured out as long as you know these two things. Oxygen is essentially always -2. And as far as hydrogen goes, hydrogen in molecules is always +1, like always. And for those two, that will get you through 99% of the oxidation numbers, things that kind of come up. Last but not least, we should be comfortable and know that the sum of the oxidation state for each atom in a compound must add to the overall charge of that compound. So let's check out an example. As I said earlier, combustion reactions are oxidation reduction reactions. So if they asked you what type of reaction this was, probably listing a redox reaction would be good, especially if they gave you the option of redox reaction, but it's technically also a combustion reaction. Notice that as we go through this, we want to assign the oxidation state for everything. I think the easiest one to identify first is hydrogen, because hydrogen is in a compound for both CH4 and H2O, we know that the oxidation state is +1, and it does not change. So oxygen is neither oxidized or reduced in this reaction. Oxygen, because it starts in the oxygen molecule, is 0 at the beginning, and then turns to -2 in carbon dioxide and in water. The oxygen molecule went from an oxidation state of 0 to -2. It became more negative. So when things become more negative, they are reduced. And I want you to kind of think about that and look at how it becomes more negative or more positive. And last but not least, carbon starts with -4 in CH4 because hydrogens were +1 and ends with +4. So therefore, the molecules, the carbon atom went ahead and became oxidized. And one of my favorite parts of this is that as the carbon moves from the left to the right-hand side, notice what happened in terms of the bonds. It formed more bonds. With oxygen. Carbon was oxidized. That's one of the other language pieces that kind of comes from this. When atoms form bonds with oxygen, they are almost always oxidized. Once again, we can see that oxygen is reduced and carbon is oxidized. If the oxidation number for the atom remains constant in the reaction, then the reaction cannot be defined as redox. Now, in terms of some of my language, I know I probably got a little redundant there, so I want to pause and answer any questions, especially in regards to oxidation reduction reactions. Hydrogen, once again, is very rarely -1. Hydrogen is only -1 in an ionic compound. Hydrogen is always +1 in molecules. So yeah. Okay, cool. So moving on. And I once again will answer any questions that you guys may or may not have. Let's go ahead and check out complete and net ionic equations. So for this, I'm going to use a reaction that I've already established, already used. And that is going to go ahead and be the lead nitrate potassium iodide reaction. We know that this is a precipitation reaction specifically. So first off, in a complete ionic equation, what we're essentially going to do is we're going to represent all of the ions in a reaction mixture during this aqueous reaction. Basically, we know that when we place an ionic compound into water, that ion dissociates from its compound. So anything that has aqueous represented or written next to it, we're going to separate it. And anything that's not aqueous, so the states of matter would be solid, liquid, or gas, we're going to keep it as is. And the way that's going to look is like this. I separate the lead nitrate, I separate the potassium iodide, and I separate the potassium nitrate, which is on the right-hand side. Notice that the lead iodide did not get separated in the complete ionic equation. And the reason that is because it is solid. It is not dissociated into the solution, and therefore it is not freely, the ions are not freely floating in the solution. Spectator ions are an important vocabulary word. Essentially, whenever they ask, or if they ask, why do we use net ionic equations? It's because the net ionic equation doesn't represent the spectator ions. That's a perfectly fine answer for why we use net ionic equations. So therefore, a net ionic equation for the one represented above will go ahead and remove the nitrate and potassium ions and just have the lead and iodide combining and coming together to form lead 2 iodide. So these are kind of a lot in terms of writing, but I do want to point out that technically, if they do ask you to write a net ionic reaction, you don't have to write a complete ionic equation. Notice that anything that's remaining aqueous on both the left and right hand side of the initial reaction, you didn't have to include. In terms of the final answer and including states, I think you just have to pay attention to language. If you were to write the chemical reaction without the states, that would be fine. A lot of teachers believe that showing these reactions without the states are still fairly representative of your knowledge. If the question obviously says make sure to include states, then obviously make sure to include states. I think last but not least, for clarity's sake, especially for your science reader, your AP reader, putting the solid on the precipitate is not a bad thing, and it doesn't really take that much time. Just saying, I know that this is the precipitate, I am putting solid next to it. All the other things we can just assume for them to be aqueous, because we can't just have freely floating ions in the air. Really, freely floating ions can only exist when they're dissolved in water. Okay, you guys ready for some stoichiometry? Woo, stoichiometry! As I'm sure all of you have an ever-growing one of these, here is our mole map. I put probably some of the, in my opinion, most important things. There's a handful of other pathways that we could add for this, but these are the main 4. And I do want to go ahead and state that density is technically fair game. So for the volume of the gas or the volume of the solution, we could move away and move towards mass again if you're given the density of the solution or if you're given the density of the gas. But that's a very unlikely. I don't see that type of question coming up. Everything that I have written on the left-hand side that is surrounding the moles of A can be surrounding the moles of B. And I'm super glad that some of you have already have this map kind of drilled into your head. Having it handy is probably not the worst idea. I do want to kind of start off fairly simply, though, and just making sure we understand the mole ratio. We use the mole ratio to convert between reactants and products in a balanced chemical reaction. It specifically identifies how many things are reacting and how many things are being produced. So if I have this chemical reaction here, 2 magnesiums reacting with 1 oxygen gas molecule to produce 2 MgOs, the way I would represent this via particles is by literally separating the magnesium ions, because that's what coefficients do. They tell you how many things that are not bonded to each other. And notice the subscript around 2, that indicates the chemical bond. The chemical reaction occurs. The magnesium ion atoms each bond with 1 of the available oxygen atoms. And because there are 2 MgOs, I literally write 2 MgOs. And I do want to point out that you can change this ratio as long as it's still a 2:1:2 ratio. I added 2 more magnesiums and 1 more oxygen gas molecule so that the appropriate ratio is present and available. Now, this might seem kind of silly that I'm doing this, but it is a possible question and it is a possibility that they will ask you to literally write 5 or 6 like circles or atoms on a test. It seems odd, but kind of be happy. You just have to kind of be good at counting when they are asking you a question that is relating to the mole ratio, okay? So what I'm gonna do is this. I have my first chemical reaction and stoichiometry problem. And the question says this: what mass of calcium carbonate is collected in gravimetric analysis if 45.4 milliliters of 1.5 molar Na2CO3 is used in an excess of CaCl2? So once again, I'm going to go ahead and write down the important information that I need for this. It is 45.4 milliliters of 1.5 molar sodium carbonate, and it's reacting with calcium chloride. All right, cool. So let's go ahead and check it out on the whiteboard. All right. Half this job is literally just like tab management. I'm like flipping through things and feel kind of cool sometimes when I move through them quickly. All right. Let's check it out. So the chemical reaction that we're looking at is going to be sodium carbonate reacting with calcium chloride to produce sodium chloride, 2 sodium chlorides, and 1 calcium carbonate. For clarity's sake, I'll write the solid next to the precipitate. And whenever they use gravimetric analysis, it's usually referring to precipitation reactions. We know that the volume and molarity of this was 45.4. And the molarity was 1.50. So let's go ahead and get started with this. If you're really good with dimensional analysis, then all you have to go ahead and do is walk your way through it using dimensional analysis. We know that there's 45 milliliters, and there are 1,000 milliliters for every 1 liter. We know that the molarity tells us that for every 1.50 moles of Na2CO3, there's going to be 1 liter. That's what molarity kind of tells us. Molarity is always going to be moles per liter. So there's 1.5 moles of sodium carbonate for every 1 liter of solution. We know that it is a 1 mole to 1 mole ratio, and that comes from the balanced chemical reaction. And then because I'm looking for the mass, I just have to multiply this by the molar mass. For every 1 mole of calcium carbonate, we have 100.1 grams of calcium carbonate. Boom, there it is. That is our dimensional analysis step. And really quickly, I won't leave this up here so I don't kind of confuse you guys. But this part right here, can be opted out if you decide to use the molarity equals moles per liter. And then all you have to do is take the moles that you would calculate and start the dimensional analysis right there. So both of those methods work perfectly fine. So by doing this, let's see here, we should go ahead and get 6.82. So really quick, and I just want to kind of talk about this fairly quickly, mostly because I think that this is a fairly, I think, straightforward concept. What if I were to get less than this? Like, this is the theoretical yield. This is how much I theoretically should get. What is the process or ideology that kind of helps us understand how good our chemical reaction was, how well our reaction was run? Can anyone help me out with that? Oh, so close. It's not percent error. It's not percent error. It does have the word percent in it, though. Percent yield, yeah. And think about it this way. The word yield is referring to a product. So if I'm talking about percent yield, I'm talking about how good my reaction was run and essentially how close to 100% I could have gotten. So if, for example, I did this chemical reaction and I collected 6.8 grams of calcium carbonate, I'd have a fairly high percent yield. I'd have almost 100% of what I should have collected. Percent error is not a equation that you're expected to memorize or know, but it is a good thing to kind of keep on the back of your mind for error analysis. Percent error is basically telling us how close our experimental value was to the expected experimental value. And you will never use percent error for stoichiometry type calculations. You will only ever use percent yield. You'll only ever use percent yield. All right, so moving back over here. I'm a hacker. Yeah, right. I wish I was better at computers. I feel like I'm okay, but like it's one of those things that I wish I knew how to code. I don't even know what I need to code for, though. I feel like that's the other thing that a lot of people are like, oh, I want to learn how to code. And it's like, well, why do you want to learn how to code? And I'm like, I don't know, because people say it's cool. Alrighty, yeah. So hopefully you got, once again, 6.82. I'm kind of quickly working our way through this because, oh my goodness, we have even more to go. Next up, which I'm sure is your favorite thing in the world, limiting reactants. So I did want to show us one type of limiting reactant problem, and kind of also discuss how not bad limiting reactants can be. I promise you guys. I know I see in the chat you guys are like, ah, it's not too bad. Okay. So as far as this goes, limiting reactants refer specifically to these chemicals having to react with each other, like they have to be present. And if you don't have one of the reactants present, then the reaction cannot occur. And the idea is that the reactions are occurring, the reaction is happening, and once again, the second you run out of one of those things, then the reaction is stopped. The limiting reactant is the substance that runs out and controls how much product is made. The substance or reactant that's left over is called the excess reactant, and it does not run out. So generally speaking, if you have a reaction mixture, the excess reactant will always be remaining there, okay? Now I want to say this is my disclaimer for limiting reactants, okay? There are about 8,000 different ways to do limiting reactants, okay? What I'm going to do is I'm going to illustrate probably my favorite way to do this, mostly because it's fast. Now, just because it's fast doesn't necessarily mean it's clear, but in terms of understanding, but it's fast. And especially with the AP test, we want to be quick with some of our methods of doing problem type things, okay? So the process for determining the limiting reactants. The first thing you should do is convert everything that you have to moles. Oftentimes you get extra points for converting to moles. So if you're really lost and you see that you have 25 grams of something, just get it to moles, and sometimes you might get lucky. But in terms of my process for determining limiting reactants, you have to do that. You're going to first convert the given reactant value to moles. Once you've done that, you're going to divide both of the values by their respective coefficients from the balanced chemical reaction. When you do this, you basically giving yourself something to compare. The thing that you compare is that the smaller value is the limiting reactant. So Perla, you asked about pressure, and you can do limiting reactant problems with pressure and compare pressure. You can do that as long as everything is under the same or constant volume and temperature conditions, okay? And you're only comparing pressure to pressure. When you guys do limiting reactant problems, and one of the biggest mistakes that I always see coming up is students always try to compare like mass to grams, or maybe in your case, pressure to moles, and you can't do that. And that's why kind of sticking with a specific pathway, this pattern that I've established for you, might be the right way to go. And if, lo and behold, you look at the next problem, I have a limiting reactant problem dealing with gases. So let's go and check it out. 7.42 grams of oxygen gas reacts with 2.75 liters of hydrogen at 1.12 atm and 25 degrees Celsius. What mass of water is produced? The first thing I want to make sure that I understand and know how to do is identify if it's a limiting reactant problem. I know that this is a limiting reactant problem because I'm given a certain amount of oxygen gas and a certain amount of hydrogen gas. And if I'm looking at this, I have reactants of both oxygen and hydrogen. I can't tell just by looking at this which one of these chemicals will run out. So what I'm going to do is this. I'm going to first convert each one of the reactant values to moles. For the oxygen gas, all I have to do for that is divide by the molar mass. For the hydrogen gas value, in order to determine the amount of moles, I have to use PV equals nRT. Once I've determined the amount of moles, I'm going to divide by the coefficients in the balanced chemical reaction. The coefficients in the balanced chemical reaction are 2 for hydrogen and 1 for oxygen. And last but not least, whatever one I have less of is going to be the limiting reactant. Now, the reason I'm going to divide by 32 for the oxygen gas molecule is because it's oxygen gas. It is the chemical that is reacting in the chemical reaction. It's not by itself, it is O2. The only time you ever deal with monatomic oxygen is when you're dealing with literally a single atom of oxygen reacting, which is technically possible but unlikely, or when you're doing empirical and molecular formula stuff. Generally speaking, in empirical and molecular formula, you're trying to figure out how many oxygen atoms you have in a bigger or larger compound. Otherwise, if you see O2 in the chemical reaction, like in the balanced chemical reaction, you're using 32. So I do all this work, I find out that I have 0.232 moles of oxygen gas available, and I find out that I have 0.126 moles of hydrogen gas available. Now that's what I have. I do want to point out that once again, that's what I have. In order to determine the reactant, a limiting reactant, I divide each of these values by their coefficients. So the oxygen gas by 1, the hydrogen gas by 2, and I get these two numbers. For hydrogen gas, it's less, and that basically tells me that hydrogen gas is the limiting reactant. Now, my question's not over. My question then asks, what is the mass of water? So what I'm going to do is this. Now that I know that hydrogen gas is my limiting reactant, I always use the value of the limiting reactant for the rest of the stoichiometric problem. One thing that's kind of scary about the process that I've posed in front of you is that if you don't use the right number, you won't get the right answer. Notice what I said earlier. I have 0.126 moles of hydrogen gas. I don't have 0.0629. The only reason that the 0.0629 is there is to help me identify what the limiting reactant was. So when I do my calculation, I must use the 0.126 moles of hydrogen because that's how much was actually reacting. Therefore, the theoretical yield of water would have been 2.27 grams. Would have been 2.27 grams. All right. So there's a couple more things that we do need to do. It's a sprint, this unit is for sure. But I'm going to and am willing to pause for a sec just to kind of answer any last minute questions about stoichiometry. And I do want to point out that what I did in terms of my question writing was I showed you a few examples. I showed you a solution stoichiometry example. That was the one with the molarity and volume. In the limiting reactant, I showed you how to use gases, and I showed you specifically PV equals nRT in order to find the number of moles. And in all the problems, I had you convert to mass using the molar mass. So I showed you 3 different types of stoichiometry questions in the context of 2 questions. All right. So titrations. Here we go. Last little tidbit. Now, if any of your teachers ended up getting into Unit 8, I am sure they talked about weak acid and strong base and weak base and strong acid titrations and the pH of the titration curve and et cetera, et cetera, et cetera. Hold your horses with that. You absolutely don't need that information. For the Unit 4 chemical reaction titrations, all you need to understand is this definition. A titration is the process of using some sort of substance of a known concentration to determine the concentration of some other substance. We most of the time use titrations for acids and bases, and we will use an indicator which does change color based on pH. But I do want to point out that you can use a titration for a redox reaction. The most common one is the potassium permanganate reacting with hydrogen peroxide. Usually indicators are used to determine the endpoint of the reaction. The endpoint is going to be specifically when the indicator changes color. For acid-base reactions, once again, that indicator is going to be pH dependent. But for redox reactions, an indicator is probably going to be one of the reactants, and you'll know that that chemical reaction is over when the reactant is completely consumed by the reaction. And all of our titrations have this general setup where we put into the burette is the long, skinny piece of glassware, we put the substance of known concentration in the burette, and we slowly add the substance of known concentration to a flask at the bottom. And in the flask, we have the substance of unknown concentration. Now, in the flask, we do know how much acid, base, that was there. We know the volume, but we don't know the concentration of the substance that's in the flask, okay? Now, burettes are funky, mostly because you have to read burettes upside down. They don't tell you how much liquid is in the burette. All they tell you is how much liquid was delivered. And you do this pretty straightforward. You do this by taking the final volume on the burette that you read minus the initial volume on the burette. And just because these are very, 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 very specific processes, burettes are often very precise, and you should make sure that you're comfortable reading the burettes very, very well. And so I have another image here to kind of show you how to look or read a burette. Notice that the 19 is up above the 20, so it's upside down, and you kind of count down from the top. So it's 19.1, 2, 3, and then it's all the way to 7. And because there's deviations every 10th of a milliliter, you need to estimate your last digit. Now, the only reason that I don't love this image here is because it says that 19.82 and 19.62 are bad measurements. And the only reason that those are bad is because they vary maybe too much from the actual measured value. The AP always gives you a range, so probably anywhere from 19.75 to 19.65, you'll be fine for that particular measurement, okay? Woo! That was a sprint. That was chemical reactions in a nutshell. I do want to remind everyone that we have lessons and lectures on a lot of Unit 4. Unit 4 is a big unit. Then you can find all of those in our Unit 4 sessions online, okay? Luckily, the last 3 units are very content specific, but they're a little bit shorter. Once again, next week we're going to be looking at kinetics. The week after that, we're going to be looking at thermodynamics, or excuse me, the Thursday after that, we're going to be looking at thermodynamics, and after that, equilibrium. Once again, while they're very specific content information, they're not as big as chemical reactions was. So anything that you felt like I missed or you need a refresher on, go check out those videos online. And I know that you guys are probably all rushing and going everywhere, but I do have one question in here, which I think I can answer really quick. I was doing a College Board question that required the use of the equation that relates G to K, but we never learned that in my class. Do we need to know how to use that for the test? No, it is in Unit 9. Woohoo! So they probably just needed that very quickly to give you a value. And you could look up that number because I think I think I know that question you're referring to. And you do need the K value for some of the subsequent questions. But for the upcoming AP test, no, you do not need to relate the value delta G to K. You don't even technically need to know what G is, except for one very minor thing in Unit 7, which, guess what? I'll talk about. If there's any other questions out there, I'll wait for about 30 seconds. Otherwise, have a great day. I know you guys probably have other sessions and things you need to do. So it's super great seeing y'all. All right. Bye, y'all.